This is lecture video 42, and we will cover how to find the length of a general curve like this in this section. We know what is meant by the length of a straight line segment, but without calculus, we have no precise definition of finding the length of a general winding curve like this. If the curve is the graph of a continuous function defined over an interval, then we can find the length of the curve using a procedure similar to that we used for defining the area between the curve and the x-axis. The procedure results in division the curve from point A to point B into many pieces, as you can see, and joining successive points of division by straight line segments like this we see in pink. Then we sum the lengths of all these line segments to find the length of the curve. So let me explain this part in more details. So we are dividing this curve into sub-segments, sub-line segments like this. So we divide this interval into n many sub-intervals. And here we will be calling this line segment as delta S. Why we are using the notation S? Because if you choose a very infinitesimal small length on your curve, it is denoted as ds. So that's why here on your curve it is ds, and if it is a line segment, you can call it as delta S. And if you zoom into this part where you have this very little right triangle, so let's call this part as delta X, and let's call this part as delta Y, because this is the X component and this is the Y component. And then from this triangle, we understand that delta S square is delta X square plus delta Y square. Okay, why we are looking at this triangle in more details? Because by concentrating on these line segments, we will try to approach to the length of the curve. We will sum the lengths of these line segments. The more line segments we have, the closer we get to the actual length, right? That's why we start by analyzing the length of this line segment. So as I said, the length of the curve, let's denote it by L, length of our curve, is approximately given by the sum of these line segments, right? Like this, where K runs from 1. So we divide this interval into K and many sub-intervals. So there are n many line segments there. Okay, we put approximately equal sign here, but we want to find the exact value of the length. That's why all we need to do is to put this limit as n goes to infinity in front of this finite sum. And you get used to this idea, like if you want to get rid of the errors, you divide infinitely many intervals. So you should send n to infinity, only then you can put here the equality sign. And we recognize this type of sums as the Riemann sums, and they can be expressed as a definite integral like this from A to B, which is our interval of the integral ds. So this delta notation is transformed to d notation when you rewrite the Riemann sum in terms of the definite integral notation. Okay, so this is the formula for the length. Now, we need to understand what does this ds means. So as we have written here, the similar Pythagorean identity works for ds too. What I mean is ds square is obviously dx square plus dy square. So you can create this little triangle also here, where this part is dx, where this part is dy. That's why we have this. And from here, you can solve ds as the square root of the right-hand side, like this. And then We can analyze the square root, the expression inside the square root, in two ways, where we divide in terms of your function, whether it is given as a function of x, y equals f of x, or sometimes your function may be given in terms of y, x equals g of y. So for these two different settings, we will try to understand ds in a more simpler form. So in this case, ds can be written as, so let me write here first. So we already write this, dx squared, dy square square root. So you can take dx square out here, like this one, okay? And then, so this is dy over dx square, can be written like this. And then dx will come out as dx squared can go out from the square root as just dx. That's why you have now inside your square root an expression like this, 1 plus dy over dx squared. So this is what ds is if your function is given as a function of x. If the curve is a continuous function f of x, then instead of ds, you can write this. Okay, so let me write this down. It is 1 plus dy over dx square root, so there is an extra dx here, okay? Or you can write it as, so this is what? This is the first derivative of your function, right? So it is f prime x squared, you have a square here, don't forget to write it, dx. And in this case, then you can, so this time x is a function of y. So instead of taking the x derivative of y function, since x depends on y, you will take the y derivative of x function. So instead of taking the x square out, you will take the y square out. So similarly, you will obtain dx over dy, y derivative of x square here, like this, times dy, because you are taking dy out in this case. So this can be rewritten as 1 plus, this is g prime of y, yeah, right? Derivative of x with respect to y is g prime of y dy. That's why now the length formula is given by, remember, we already understand this. Definite integral length is given by the continuous sum of all those ds's, where ds is a very small part of your curve. And ds is given by either this form or either this form, right? So this gives us the exact formula for the length. And it is like this, maybe. So let's write this in the middle, like a to b ds, and it is written as in this form. 1 plus f prime of x squared dx, or in this form, 1 plus g prime y squared. So there is a square here, let me emphasize it, dy. And this happens when your function is a function of x, and this happens when your function is a function of y. This. So, and in this formula, you are integrating with respect to dx, and in this formula, be careful, you are integrating with respect to dy. So this explains where does this formula come from, right? So we just covered it. Okay, let's apply the length formula on this example. We want to find the lengths of the curve given by this expression over this interval. So let's try to write the expression for the length. So we will be using this formula from 1 to 8. This is the upper level bounds for our curve. 1 plus This is the first derivative of our function. You will square it, then you will integrate with respect to x. Okay, so we need what? We need the first derivative of our function where the function is given like this. So let's compute it. This is our f of x function. Y is given by this formula, 4/3 minus 3/8 x 2/3. So what is y prime, which is the first derivative of your function where your f of x is this expression? You can easily derive it. 3/4 times 4/3, then you will subtract 1 from the power 1/3 minus 3/8 times 2/3. Subtract 1 from the power like this, and then you have very nice simplifications, as you can see, like that. And this is simplified as 4. So first derivative function is what? It is x to the power 1/3 minus 1/4 x to the power minus 1/3. Okay, so we need to, okay, let's insert this first derivative function to our length formula. It is from 1 to 8. Let me choose blue color again. It is from 1 to 8. 1 plus square of this expression, right? Minus 1/4 x to the power minus 1/3 squared, and I close the square root dx. Let's try to compute this integral now. Okay, what is this square? Let's first compute it. I will just compute the square expression, okay? So this is x to the power 2/3 minus 1/2 x, just 1/2 because you are multiplying this with this and then by 2 so that you obtain minus 1/2, and then plus 1/16 x to the power minus 2/3. And let's take also this 1 to here. So I'm trying to compute whatever we see inside the square root right now. What is this? So 1 minus 1/2 is just 1/2, and I have this plus 1/2 and this one plus 1/16 x to the power this. Okay, now if you look at this expression really carefully, you understand that it is a perfect square. So how it is a perfect square? So it is the square of this expression, in fact. So you can easily verify that if you consider it carefully. So this expression is the square of this expression. That's why now inside the square root, we have a complete square, which will help us to compute things. So this square, inside this square root, we have this square. So square root and square will cancel out so that I can just write this inside my integral notation without any square roots. Okay, so these are all power functions now, which can be computed easily, which can be integrated easily. So add 1 to the power, divide by the same power. Similarly, add 1 to the power, divide by the same power, and then insert your upper lower boundaries, x equals 1 to x equals 8, okay? So if you insert 8 first and then 1 and then take the difference, you will obtain this result as the length of your curve. Okay, so let me write here what we have found. 93/8 is the length of the given curve. Okay, what is this curve? It is given by this formula y equals f of x formula. So from which point to which point? We were interested in point 1 to point 8. So the length, this length is computed as 93/8, length of this curve. Okay, so this is a nice explanation of how we can find length of curves. We try to apply this formula. That's why we start by taking the first derivative and then we continue with the computation of the integral. Okay, let's move on. Look at this example, please. Okay, before that example, I think I need to explain this part to you. Okay, we already go over this above, where you have x equals gy curves. Okay, this time your curve will be given in terms of y-axis, like x equals g of y. Then you can use your length formula with respect to y. Okay, that's why this is the y derivative of x function. Okay, x derivated with respect to y, where x is g of y, can be written as the g prime of y. So we already covered this formula above. Now we will apply it on this example. Find the lengths of the curves. So here, as you notice that the curve x is given in terms of a y function, because you see the y dependency here. That's why the length of the curve is in fact from this point to this point, minus pi over 4 to plus pi over 4. Remember the formula, it is 1 plus dx over dy squared, and we will integrate with respect to y. Okay, here is your x function, and I want to find the y derivative of it. Sorry. So let's try to integrate, derivate this x function with respect to y. So with respect to y of this function, which depends on y, right? Secant to the power 4t minus 1 square root dt. Okay, this is an integral in terms of y, and then you are allowed to derive with respect to y also. And first integral, then derivative should remind you which theorem, fundamental theorem of calculus part 1. All you need to do is to insert this variable for the variable t here, where this is your function f of t. Remember the fundamental theorem of calculus. So that's why the result is directly f of y, where y is inserted for the expression t there. So this is secant to the power 4 y minus 1 square root, okay? And now this is y derivative of x. We will insert this to here to find the length. Okay, 1 plus square of this thing. So secant to the power 4 y minus 1 dy. And you see we have simplification here. Then minus pi over 4 to pi over 4. We are trying to integrate secant square y dy, okay? And what is the integral of secant square? Now, you should consider the antiderivative function of this thing. Tell me some function whose derivative is secant square. So it is obviously tangent y from minus pi over 4 to pi over 4. If you insert these upper lower boundaries, so minus pi over 4, you will find the result as tangent of 45 degrees is 1, tangent of minus 45 degrees is minus 1, so that the result is 2. So the length of this given curve by using this length formula is computed as 2. So I stop here for the length lecture video.